This conference will now be recorded.
Very good evening, students. So today we'll be revising electrostatics, Coulomb's law. So we have already discussed this chapter, or we have already covered this chapter thoroughly, where we had discussed electrostatics since beginning. Each and everything we have already discussed. So here, this revision session, what we are going to do, we are just going to take the topics of particular chapter and we'll take intricate concepts, and from there, based on that concepts, we'll try to solve various typical problems which are not very easy, which are maybe mild, hard, or harder, or advanced questions from particular topics, and those questions will be from various competitive exams as well. So today we have picked up from electrostatics Coulomb's law. So this is very simple, but when you go for solving problems, then in some cases we actually stumble. Okay, so let us first recap a little bit about Coulomb's law, and then we'll solve few problems on this. So what is Coulomb's law? So first of all, this is electrostatic. That means charges are static charges. Okay, so there are two or more than two charges, suppose Q1 and Q2, let us say Q1 and Q2, and obviously this Coulomb's law actually is valid for point charges. Okay, so Q1 and Q2, first I'm not taking the sign as well, I'm just taking in general positive sign. Okay, and say the distance between them is R. Okay, so Coulomb's law actually states about the electric force. It talks about electric force between two charges. Okay, between two charges. So what it does, or what it states, so Coulomb's law states that electric force exerted by one charge particle on another acts along the line between the charges. So it acts always along the line, either this way or that way. Obviously, we'll see electric force or this electrostatic force or Coulomb force actually are action and reaction. It always acts in pair. We'll see that also. First of all, let us understand the statement of this Coulomb's law. So if we have two charges Q1 and Q2 and their line joining is this one, so according to the Coulomb's law, the force exerted by one on another will be always acting along the line of the force. It varies inversely as the square of the distance separating the charges, and it is proportional to the product of the charges. So if I say the force is Fe, electric force, and with vector sign, it is directly proportional to the product of these charges, and it is inversely proportional to the square of the distance. Okay, so if we combine these two, see, if we combine these two, electric force, I'm just taking the magnitude for convenience. So see, this will be proportional to both this together. If we write, how do we write generally? We write Q1 Q2, product of that, directly proportional to the product, and inversely proportional to the square of the distance. Okay, Now anyway, this is not going to help us. We have to always go for an equation. So magnitude of this, if I write equal sign, there should be one proportionality constant, let us say that is k, and I will obviously tell you what is it is. So this is actually the Coulomb's law or Coulomb force. See, now come to the point. If we have two same sign charge, signs of the charges are same, when the sign are same signs, okay, that means both are q1 is positive charge some value and q2 also is positive, then this force will be actually repulsive in nature. What is this repulsion? See, if I say force on F1 due to, sorry, force on Q1 due to 2, I should write in this way, okay, and with a vector sign like this. So since it is repulsive force, so force on Q1 due to Q2 will be just pushing force. This repulsion means pushing, okay, this will be pushing in this way, right? So this is the force F12. If I just ask the opposite, the force on Q2 due to Q1, so this is F12, and this side it will be F21. That means the force on Q2 due to Q1. Okay, so you can see the directions of the forces are just opposite because these are actually repulsive force. So repulsive. So same sign, repulsive force. Okay. Now, if the signs are different, so signs are different, magnitude will be the same, but directions will be different. Okay. So in case of attractive, see, if suppose this is a negative charge, Q1, and Q2 is positive, I'm not going to discuss this magnitude. Let me first tell you the direction and vector form of this. I'll tell you. So suppose this is a positive one. So what will be the direction of the forces? Suppose F12, if I write. So in this case, you know, F12 will be this way because this is F12. Because this Q2 will be attracting, it is pulling force now. Similarly, on this Q2, the force on Q2 due to Q1 will be in this direction. It will be actually pulling each other. They will be pulling each other. So these are repulsive. This is actually attractive force, attractive. And if both are positive, then these are actually repulsive. So I hope this is fine so far. Now, see, if I want to write vector form, okay. So if I want to write vector form of this Coulomb's law, then we must define. So suppose Q1 is here and Q2 is here. So we must actually define position vector with respect to some arbitrary origin. So we must define position vector. Suppose this is R1 with respect to this origin, and position vector of this is R2. So this is how we need to define. Okay, this is R2. Position vector of Q1 is R1 and this is R2. So then see, how do we write the vector form of this Coulomb force? You know, for that case, suppose I want to write force on Q1, force on, let us first take the repulsive nature, Q1. So by the way, what is this position vector? So let us say this is R12. Okay, if this is R12 vector, see, I can just do one thing. I can take direction for the time being. Let me take this direction as this. Okay, so R1 plus R12, just by using vector triangular rules of vector addition. So we can write this is R2. Okay, so look from here, what we write R12 to be R2 minus R1 according to my direction. I would have taken this direction in opposite direction also. So look, if I just take just reverse the direction here, it will be R1 minus R2. That's all, nothing else. Okay, I think we should go with indices. Let us just reverse the direction. Let me just go with this so that it will not be a confusion. So it will be R2 plus R12 is equal to R1. Okay, so R2 vector plus R12 vector. This let us write this to be R21. Better to write R21. So this is R21. Okay, so this is R21. Mhm. So if I do this, then I get this is R1. Okay, so look, then here we get R21 to be equal to R1 minus R2, R1 minus R2. Okay, so R21 means R1 minus R2. All right, so this is, see, as I showed already to you, that these are just, see, if I reverse the direction, say R12, so R12 will be R2 minus R1. Okay, R2 minus R1, and this is nothing but minus of R1 vector minus R2 vector, right? So this would give you minus of R21. Okay, so these are the things. Now look, in this case, if I write, suppose both are positive, for the case of repulsive force, what we write, force on Q1, this is positive Q1 due to Q2, that is also positive. So in this case, what we should write is this, force on this. So you look here, force will be in this way, right? Repulsive force, 1 2. So I should write, so K is the constant, I'll talk about this. So Q1 Q2 by, see, now it will be actually, the distance between these two is actually, now see, if I say R21 here, R21, okay, so if I want to write in terms of square, then let us take this as mod. Okay, but what is the direction? What is the direction? The direction is R21 unit vector I should write. If you want to write in terms of vector, then you have to write Q1 Q2 by R21. See, I want to write this as vector, so this mod square. So here, see, unit vector means a vector, sorry, 2 1 or 1 2 whatever it is, 2 1 divided by its magnitude. Okay, we have this square, so what we are getting, K Q1 Q2 divided by, see, this is R21 mod of that whole cube into R21. Okay, so this is how you should write in terms of vector. Okay, yeah, I'll just go with the other one. Okay, so see, if I say force on Q2 due to Q1. Okay, so what we should write? We should write F21. So this is, see, the direction of the force will be in this direction. Okay, so I can write R12 or negative of R21, whatever we think. So we will write directly here Q1 Q2 by this. See, it is, let us say this is R12 whole square. We can write directly as cube here. So either we can write R21 cap vector, or we can write this is cube, sorry, this I should not write cube. If I write cube, then we have to write vector in the numerator. So this I should write R12. Okay, so this is how we have to write in terms of vector. Okay, so far so good. Okay, we'll just discuss this constant K. What is this K? So this K is actually the proportionality constant, and you know, okay, I'll just erase this part. Now, the Coulomb force, I'm taking the magnitude Q1, Q2 by R square. Okay, so in this case, what is this K? Actually, K is equal to 1 by 4 pi epsilon naught, where this is free space permittivity. It has its value, but we generally write this value approximately 9 into 10 to the power 9. And what will be the unit? Unit will be Newton meter square divided by Coulomb square. Okay, so this is the unit. So this is actually, see, we are talking about electric force between these two charges. See here, Q1 and Q2 I have taken. This Q1 and Q2 in vacuum I have taken in vacuum. So there is only air, nothing else inside this. Okay, vacuum. Sorry. So only vacuum. Okay, or we can say empty space here. This is empty space. Empty space. So in empty space, what is there? By default, we say there is air. Okay, or free space. So that's why this permittivity due to free space comes here. But suppose these two charges are put inside the water, some other dielectric medium. So in case of dielectric medium. So if we put the charges inside dielectric medium, then how does it change? So that change we'll discuss. So how is it differing? Okay, we'll tell you what to do in that case. So Coulomb force, Coulomb force in dielectric medium. Okay, so Coulomb force in dielectric medium. So what we should see, or we should try to understand what happens for Coulomb's law in dielectric medium. So in case of dielectric medium, what happens for the, see, in that case, we can no longer use this just simply epsilon naught. What we have to use is epsilon so in that case we have to use epsilon, and epsilon will be epsilon naught into epsilon r. Okay, so relative permittivity will come into picture. Okay, so relative permittivity will come into picture. So in that case, we'll have few numerical example in that case, and how it modifies, we'll see that. Okay, so suppose, okay, let me just write it here itself. First of all, in vacuum or in free space, how Coulomb's law look like in free space. So in free space, Coulomb's law look like, so this is magnitude K. Okay, let us not write K now. We'll write in full. So this is Q1, Q2 by 4 pi epsilon naught R square. This is free space. In dielectric medium, what happens, in case of dielectric medium, since, say, in presence of these two charges, so suppose there is a dielectric medium in between, so these are also charges, right? So these charges will be induced, so there will be electric field, corresponding electric field due to both the charges. So there will be actually some induced charges in the dielectric medium. So in that case it is not going to be straightforward. Okay, so in that case, so actually this value 1 by 4 pi epsilon naught, it has a perfect value nearly 8.99 into 10 to the power 9. This we have taken approximately that. Okay, this is a Newton meter square per coulomb square. So this is the value. But in dielectric medium, what happens? Dielectric medium, so this force will be Q1, Q2 by 4 pi epsilon square, sorry, epsilon r square. So what is this epsilon? Epsilon, if we put Q1, Q2 by epsilon naught, this is epsilon naught, epsilon r. Actually, what we can do. So this we can write as epsilon naught, epsilon r, sorry, epsilon r and epsilon naught See, we can just do one thing. This we can, in fact, we can just write. Okay, this is relative permittivity, nothing else. Okay, so this is r square. You look here. So this particular part, q1, q2 by 4 pi epsilon naught r square. This is my original force. Now it is f prime. Okay, so this is into 1 by epsilon r. So this is relative permittivity. Okay, so you can see we are getting f by epsilon r. So if sometime there is a multiple charge type question that two charges are kept in free space, and then the electrostatic force or coulomb force between them is F, and if the same charges are kept inside a dielectric medium of relative permittivity relative permittivity of that medium is epsilon r, then you must write the force to be F prime is equal to the force in free space divided by epsilon r. And or sometime it you may be asked whether the force in the dielectric medium will be less or more than the free space, etc., etc. So this is the thing. Okay, I hope this is clear to you. So we'll just move on to few characteristics of this Coulomb force. See, first of all, the important characteristics of this Coulomb force is actually it is it actually obeys superposition superposition law or principle of superposition. Okay, so what does this mean? Suppose I have I have q1 charge here, and then I have q2 here, q3 here. I'm just writing, giving the positions. Okay, so here q3, or maybe somewhere here q4, etc. are there. So I have to find out force. So force on q1, force on q1 due to all other charges. So how do you find out the force? So it said, see, the principle of superposition says that in this case, so you can actually calculate the forces individually. Okay, individually without like with neglecting the presence of others. Okay, you can neglect the presence of others. Suppose I want to calculate the force on q1 due to q3. I'll just consider these two alone without considering the presence of others. So this is simple. This is very simple. Now, if I want to calculate the force on q1 due to q4, so I just consider this q1 and q4 alone. Okay, alone we can find out. So similarly, q1, q2, like that. If I write f1, f2 and f3 are, sorry, f2 and f3. So f1, f2 and f3, that forces on this individually when you calculate. Okay, so between q1 and q2 this is f1, between q1 and q3 it is f2, and between q1 and q4 is f3. Then see, we can take the vector sum. Okay, vector sum of all those forces, because these forces are Coulomb forces are vector quantity. So we have to take vector addition of all those, or vector sum of all those forces. Okay, so it is written here. So net force could be found out if you have a system of charges. So force on a particle due to all other can be found out uh, using the superposition principle. So in that case, what you have to do, you have to take the reference or on which the uh, force is acting, and calculate the forces acting on that particular charges due to each and individual charges, and after finding out the forces, individual forces, you can sum up. And since force is a vector quantity, so you have to take vector sum of that. So this is principle of superposition. Okay, so we'll go to another important concept, that the electric force is actually, it occurs in actually pair, just like your gravitational force also, we know gravitation. See, if there are two masses m1 and m2, they will mutually attract each other, isn't it? So mutually they attract each other. In this case also, they see in this case like attraction by this, attraction by this, they're acting together, isn't it? Attracting together. So they are actually acting at the same time. So in this case also, the reaction forces like this are actually called interaction. Okay, electrostatic interaction or electrostatic interaction, we can say. Electrostatic interaction is always in pair. Suppose I have q1 here, I have q2 here. If I have to find out force due to this, there must be equally probable force on this. Okay, so and these two will have the same magnitude, by the way. Okay, so this will, so suppose repulsive force, so they will actually push each other, they will just push each other, they will push each other, and maybe there will be a possibility of equilibrium. Okay, if the forces are equal in magnitude, sorry, charges are equal in magnitude. So electric forces is conservative in nature. So electric force, electrostatic force is conservative in nature. Electrostatic force. I hope you have understood, or you know the what is conservative force will. Electrostatic force is a conservative force. What is this conservative force? We have already discussed. So for conservative force, closed path integral will be 0. Okay, work done in a closed path will be 0. Work done in a closed path will be 0 due to electric force. And then work done does not does not depend on does not depend does not depend on what? It does not depend on path. Work done does not depend on path. It depends on the only on the end point. Since in a cyclic process, so end points are at the same point, that's why there will be zero work done due to this kind of central force. Okay, central force or conservative force in, okay, so conservative force. So coulomb force actually is a conservative force. Now I'll just talk about one interesting theory. This is related to uh, vector only, but this will help you to solve very many numerical problems. Will obviously show you how you can apply this Lem's theorem. So you know what is this Lem's theorem? So according to Lem's theorem, let me write. According to Lem's theorem, if three concurrent forces, three concurrent forces F1, F2 and F3 are in equilibrium. In equilibrium. Okay, they are in equilibrium, or if equilibrium in the sense F1, sum of them will be 0. Net force will be 0. If this is the case, then according to Lem's theorem, we can write F1. Okay, so F1, so this is actually magnitude by sine alpha. That means the angle between alpha is the angle between 2 and 3. When I take 1, F1, I have to take the angle between the other two forces. Other two forces are this F2 and F3, that is sine alpha, sine of the angle between other two forces. Like if I take magnitude of this F2 divided by, I have to take the angle between 1 and 3. Angle between 1 and 3 is beta. So sine of beta is equal to mod of this is divided by sine of, obviously between 1 and 2 angle, this is gamma. So this is actually Lami's theorem. Okay, so this is Lami's theorem. We'll obviously take up example to understand this. Okay, all right. So if some cases we know there are two charges. If some cases, so this is a separate thing I'll talk about. So if suppose some cases the coordinates of the charges are given as x1, y1 and z1 if they are given. Okay, and for q2 coordinates are given, then it is easier to find out the position vectors of each. Okay, position vectors of each. Suppose for this case r1 we should write in this way, that x1 I cap, y1 j cap and z1 k cap. Okay, for this also we should write r2 is equal to x2 I cap plus y2 j cap plus z2, sorry, y2 j cap and z2 k cap. Like this we should write. Okay, so once you get this, then other things you know how to write down the vector and all. Okay, so in that case, see, we can write force F1, suppose this is Q1, so K, let me write Q1 Q2 by R1 R2 vector mod of that R12. This is actually a vector. Okay, so what we can do from here, see, this R1 to vector will be R1 minus R2. This vector will be, see, x1, sorry, x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 into k cap. Okay, this is how. All right. Now, okay, so with this short recapitulation of few important topic about, or important concept about Coulomb force, let us try to get some numerical example and solve them and learn many more intricate concept in this itself, like how to solve. So for like, this is very simple, theory is very simple, but when you solve problem it is little difficult. We'll show you, like I'll show you how difficult it could be in various cases. Okay, so let us first take a very simple problem here. What is the smallest electric force between two charges placed at a distance 1 meter? So the smallest electric force means you have to take the fundamental charge. So what is the fundamental charge? E, that is 1.6 into 10 to the power minus 19. This is actually the smallest charge, or unit of charge actually it is said. Okay, or the quantum of charge. This is the quantum of charge. Like in case of light, you have light quantum, and each quanta has energy h nu. Similarly here, the charge quanta is there. If I suppose and that uh, unit of that quanta is 1.6 into 10 to the power minus 19 coulomb. Okay, this is the fundamental charge. So smallest electric force when we are talking about, then we have to actually find out the force, electric force between these two actually. Okay, so it is very, very simple, nothing much. So here E into E divided by 4 pi epsilon naught. Distance is 1 meter, 1 meter square. So in this case, so this will be obviously Newton. Let me write 1.6 into 10 to the power minus 19 whole square, or let me write separately 1.6 into 10 to the power minus 90. Okay, okay, so and also 1 by 4 pi epsilon naught, this will write approximately 9 to 10 to the power 9. Okay, and 1 meter anyway, in the denominator there will be 1, that doesn't matter much. So 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 here the value will be how much? So if you just multiply all these values, so what you are going to get 2.304 into 10 to the power minus 28 Newton. Okay, this is the smallest force. We'll go to the next problem. So this problem, it is very common problem. We'll just try to solve it. Very simple. Three charges Q1. See, Q1 is here. These are Q2 and Q3. So Q2 is here. This has a value Q2 minus 2 microcoulomb and Q3 3 microcoulomb. Okay. So you have to find out the net electric force acting on the charge Q1. So I'll actually solve this in two methods. Okay, let us say this is method 1. We'll solve this in two methods. So method 1, let us see what happens. So we have seen that Q1, let me write it here. Q1 is 1 microcoulomb. Q2 is this, and Q3 is 3 microcoulomb. Okay, so this is negative and this is positive, this is also positive. So this is positive, this is positive, this is negative. So directions of the forces are important and also magnitude. So in this case, look, the force on Q1 due to Q2, I'm just writing this is in this direction, F1 2, this will be in this direction, and the force on Q1 sorry, it was muted. Okay, I'm back now. So the force, see, in this case, the force, let me just check one thing. I see. This is actually positive, and this is also positive. So these are actually positive. I'm sorry, these are positive. This is negative. Okay, this Q2 is negative. I'm sorry. So this is negative. So anyway, the attractive force is in this direction, F12. But what about F13? This will be in this direction. Okay, F13. So what we can do, we can actually uh, see, we can draw the force here. This is F12 and this is F13. So you can get the direction or the net force along this direction. Okay, this will be the net electric force on Q1. So what are the magnitude? Let us first do one thing. Let us find out the magnitude F12. What is the magnitude? So Q1 Q2 by 4 pi epsilon naught. And what is the distance? So this is equilateral triangle of side 1 meter. So this is 1 meter. So there is nothing else. Let me just write it. So 1 by 4 pi epsilon naught. This will be 9 into 10 to the power 9. Okay, approximately. Q1 and Q2. Q1 and Q2, I am taking the magnitude. So I'll take this 2 into 10 to the power minus 6 divided by 1 meter square. So this doesn't make any difference. Okay. So what is the magnitude here? Magnitude of this force, if we calculate, it will be approximately this. This is this one. This much Newton. Let us find out the magnitude of this also. This force also. Similarly, this is anyway. I can just directly write 9 into 10 to the power 9 and say 1 3. So this will be 1 into 10 to the power minus 6 divided by 1 square. So this will be 2.7. This is very simple, straightforward calculation, and nothing much. 10 to the power minus 2 Newton. So if we want to get the, see here we have got this superposition principle, right? I have to find out F net. This is superposition principle. So I should find out F1 2 plus F13, this sum. And this vector sum can be done in two ways, like parallelogram, law of parallelogram of vector addition, or law of triangle. So here in this case, law of parallelogram we can use, or anyway both are equivalent. So in this case, what is the net force? You look, I have shown you here. So this is F12 and this is say F13. Okay, say F13. So in this, so this is F12. Look, then F net, I'm just taking the magnitude now. F net will be found out. See, we write, see, what is the angle between these two forces? This is 120 because this is 60. Equilateral triangle 60, and this is, see, this is 180. So you just reduce this much. So 120. So what will be the force then? F1 square plus F2 square plus 2 F1 F2 cos of 120. Okay, and see if we do the calculation properly, how much we are getting. So if we do the calculation properly, then we must get the value of net value. We must get, see, sorry, this is, yes, so 2.38 into 10 to the power minus 2 Newton. So now what is the angle that makes with the force F12? or horizontal force. So this, suppose that angle is alpha, so we can write actually tan alpha is equal to how much? Tan alpha we can write, tan alpha we can write in this way, that if 13 sine 120 degree divided by f 12 plus f 13 cos of 120 degree. So just I have applied the formula what we have learned in vector. Okay, so here this is 2.7 into 10 to the power minus 2 Newton and divided by these things are there. So if we just put the values, see this f12 is 1.8 into 10 to the power minus 2 plus f13 is 2 into 10 to the power 10 to the power minus 2 Newton into cos of 120 is minus half. So if we do this calculation and find out alpha, it will be nearly 79.2 degree. Okay, obviously this requires maybe a calculator, but in your exam what will be given is straightforward, so that you doesn't require any calculator. Okay, so this alpha is the angle between the net force, or the net force makes the angle alpha with the line joining the forces q1 and charges q1 and q2. Okay, so today what I'll do, I'll just go for the second method. Okay, second method quickly. I'll show you how to do the second method. Okay, this is method 2. Method 2. So in case of method 2, see what we can do. We can actually think this charge q1 is at origin 0 0 0, and this is, see this is 1 meter, right? So this could be at 5. So this has uh, this say x coordinate for this q3 charge, x coordinate for this is 0.5 meter, y coordinate is this one. So let us say this is not okay, actually you can find out what is the height, you know that. So this is suppose a by 2, this is anyway a, so what is this? So a square is equal to a square by 4 plus some x square. So x square we need to find out, that is then 3 by 4 a square, so root 3 by 2a. So this is x. So this height could be found out, and that is, suppose here we have calculated this to be this much, and z is 0. Suppose this is in xy plane, and this is having y coordinate 0, and this is x coordinate 1 meter, y coordinate 0, and z coordinate also 0. So can we find out the position vectors, as I said, as I was showing you how to find out position vectors? Can we find out position vectors? So suppose, see, this is origin, so this is, I say this is r1 vector, this is r3 vector. Okay, and yes, so r2 vector, let us say this is r2 vector, so r1 and r2. So what is r1 then? R1 vector is, see, r1 vector is this one, I cap. Okay, only I cap, right? I cap. And what is R2 vector. So this is 1 into I cap, say. What is R2 vector? So it is actually 0.5 I cap plus 0.87 J cap plus 0 K cap. Okay, that means this is 0.5 I cap plus 0.87 J cap. Okay, these are two vectors. So look, the forces what we write here. See F12. So along x-axis, let us take that as F1 itself. Okay, F1. This along this F1, and this is F2. Okay, F2. We'll write that. So F1, I can write F1 vector. So 9 into 10 to the power 9, that is fine. All right, Q1, Q2. Okay, Q1, Q2, what we should write else? See Q1 and Q2. So Q1, Q2, this is charges 1 and 2, it was 2 into 10 to the power minus 6. Q1, Q2, 1 by 4 pi epsilon naught, R square we have to write, isn't it? So this will be R1 square, R1 cube into R1 vector. So this will be, see, R1 cube means this is 1 meter. So this is anyway 1. So this is going to get you this much Newton, and that is along R1. Along R1 means which direction it is? It is actually along I cap direction. Okay. Similarly, if I go to calculate the force F2, let us say this force is F2. So this force, so similarly, it is 9 into 10 to the power 9 into 3 into 10 to the power minus 2 divided by, see this vector, we have to take the mod of this. See, mod is actually square root. Actually, this will be, see, cube if I write, then I have to write 0.5 square plus 0.87 square whole to the power 3 by 2. 3 by 2. And this is a vector over here. You look, this vector we can write 0.5 I cap plus 0.87 J cap. Okay, this way we can write, and see if we just do the calculation properly, then okay, just a minute. Yes, so here actually I have just done one small thing. Okay, so here will be minus sign, with a minus sign. Okay, here it will be with a minus sign. Here this will be minus sign because it is in the opposite direction. Okay, so ultimately if we just calculate, we'll get this force in this way, 0.45 I cap minus 2.349 J cap whole into 10 to the power minus 2 Newton. Okay, so once we, I'm sorry, this is actually the sum one. Okay, so all right, so today actually we are a little bit out of time, so tomorrow we'll discuss this part again, this method, second method. Actually the value will be, I'll just write the final values. Final value should be the same what we have got in the other method also. So in this case we can write in terms of vector. Okay, so I hope you have understood the method. Tomorrow we'll take up numerical examples like that, so that it will be very much clear. Okay, all right, so thank you for your patience. Bye for today.